So the great part about the unit that we're headed to is everything you need to know is going to be provided to you on the formula sheet. This is the first time the formula sheet actually shows up. So what I mean is, generally mathematicians don't find this kind of thing significant, like memorizing these facts, but how you apply them is the significant part, right? So all the stuff I'm about to throw at you, you're going to see on a formula sheet. So the first part is the cosecant, and one of the identities we talked about is it's the reciprocal of the sine. The secant, does anybody remember what one that connects to? Yeah. Good. And then cotangent is connected to the tangent of x. The other things that we said already that we found on the unit circle was that the tangent was the sine of x over the cosine of x. So how do you think I could write one for cotangent? Good. Yeah, it's just the flip version. Cosine over sine. So that's the first set of identities that we're going to work with today, and I'll show you how we can simplify some of this trig stuff down. Now, the real learning curve here tends to be fractions. So if you're having troubles with fractions, we need to talk about practicing some of your fraction skills. So that's where we're going to start. Does anybody know, like, how do you deal with this kind of monster, right? Like, that is an awful fraction to work with. Anybody have a strategy? Yeah.
You multiply the reciprocal of the sine x over cosine x?
Yeah, that's going to, I'm going to do what David just suggested, but I'm just going to show you a step in the middle so you see. This bar, it means divide, right? When we say you have 3 out of 5, we're saying 3 divided by 5. So for some reason we forget that. And if I want to rewrite this question, I could call this cosine of x over the sine of x divided by the sine of x over the cosine of x, right? And now it's not so scary because I don't have complex fractions to deal with. So now I'm going to do what David said, is you flip and multiply, but you might not have made the jump all the way to the end like he did. And that's going to end up giving us cosine squared x over sine squared x. Now, how do you think we could rewrite this? Does anybody? Yeah, that's great. This is actually the cotangent squared. So we've just simplified this down to one trig ratio. From all of these, mess of fractions, down to the cotangent squared of x. So you try it now. There's a complex fraction here to work with. See if you can figure out and simplify this expression down. So at this point you might be like, well, I don't know how to go any further with this. But one of the ways that we can break this down even further is generally when we don't have any other identity to use, the best strategy is to go back to cosine and sine. Everything that we have can be written in terms of sine and cosine. So if we have nowhere else to go and we can't think of what to do, if you revert all the way back to simplest terms of just sines and cosines, then we can try and change the problem further. So let me show you what that looks like here. I'm going to rewrite this as tangent becomes sine of x over cosine of x. And I'm going to have this mess again, which is 1 over sine of x and 1 over cosine of x. Now, I can feel that some of your heart rates just jumped when you saw that fraction come at you. But remember, that's okay. We can rewrite that so we don't have to deal with a complex fraction. I can call this just a divide sign. Now, there's another strategy that I want to show you, and it's my favorite. And I'm going to start like easing you into doing it this way. But what we're trying to do is we're trying to knock those denominators out. We'd like to see them go away. One strategy I can do is if I multiply on the top and the bottom of the fraction at the same time, then I haven't changed it. Like if I was to go like this and say times 5 divided by 5, I multiplied by 1, which doesn't change the expression. So I'd like to multiply by something clever that's going to remove all these bad fractions. And the way I do it is I look at the denominators. Oops. I look at the denominators, and I take the lowest common denominator for the bottom times the lowest common denominator for the top. So it'd be, in this case, there's only one denominator, so I'm just going to multiply by sine x, and there's only the one denominator here, cos x. And again, you don't have to do it this way. I'm going to do it a few times with you today so you get to see this strategy. But what's going to happen here is if I multiply the top by sine x over cos x, that's gone, and all I'm left with on top is cos x. Then when I do it on the bottom piece here, cos is gone, all I'm left with is sine of x. Okay. So it's one way I get out of the fractions, and I think usually it works out a little quicker. So what I'll have left then in those pieces is the sine of x over the cosine of x times the cosine of x over the sine of x. And it's probably not clear to you looking at the original that we had, but this is actually equal to just 1 because those cosines and those sines are all going to divide out too. Okay. Now, it's important when you do this stuff, and you're going to see again when we work on like log equations and other things like that, we can change something and give it a new form. But when we do that, we may lose part of the problem. And one thing we lose here is 1. There's no place where 1 is undefined. But in the original problem here, that tangent graph, you should remember it. There's places where tangent's undefined. That's a problem. So we can't just say that this simplifies down to 1, because that wouldn't be true. The original is not defined everywhere, and 1 is defined everywhere. So what we have to do when we say state the restrictions is go back to the original and figure out what's wrong with the original. What do we have to preserve? So if you remember, does anybody remember where the tangent has problems? Yeah. So cosine can't equal to 0. I'll put that in our margin here. I'll use a different color. So if tan x, I can't have cos x equal to 0. Running out of space, so I'll move it down. Does anybody remember where that happens? Yeah, pi over 2. So the first thing I'm going to put in here is x can't be equal to pi over 2 and any multiple after that, right? So yes, the value is 1, but you cannot do this at pi over 2 plus any multiple of pi. Like pi over 2, 3 pi over 2, 5 pi over 2, 7 pi over 2. Okay. There's still other problems here, right? The secant is also got a problem, and the cosecant has problems too. Secant has a problem because it's going to be 1 over the cosine, and cosecant has a problem because it's 1 over sine. Now, secant of x, if that's 1 over cosine, then we've already taken care of that problem here. We've done the work, so we don't need to repeat that a second time. We've already made sure that cosine won't be equal to 0. Okay, but then the other problem is this piece here. It says, okay, cosecant is 1 over sine. So what do we have to stop from happening here? Yeah, sine x can't be 0. Does anybody remember where that happens? Yeah, so 0 pi, 2 pi, 3 pi, so any multiple of pi. So we would just write it down like this. Now there is one more problem. Oh my god. So many problems with this question. Does anybody think they know where the last problem is? Secant x over? Yeah. So you have to remember there's another fraction in here. This whole thing is one fraction, that cannot equal 0. So if I don't want this fraction to equal 0, the secant of x can't equal 0. Or, boom, I have another problem where it would not be defined. Okay, so secant x, where does that equal to 0? Okay, so here's the graph of secant. If you wanted to take a look, where does it equal 0? Nowhere. Yeah, there's no spot where it touches. What would you have to do? You'd have to be solving this equation. You'd have, if secant of x equaled to 0, then the cosine of x has to be equal to 1 over 0, or that it's undefined. Cosine of x is not undefined. It's defined everywhere. We can never find this answer. Since the answer doesn't exist, that means we'll never have that problem. So in this case, we don't have to worry about it. No problems here. These are the only restrictions on that problem. Okay. Now that was like the mother of all restrictions. That would be a considerably difficult question for you to deal with. But hopefully it sets the stage where you're thinking, where do I find my restrictions? Okay, so I want you to go with your neighbor and look at this previous one. Your first job is to figure out how many fractions are you going to have to look at. Okay, how many fractions are you trying to make so that you don't divide by 0? Okay, once you do that, then we'll talk. All right, so let's see. How many fractions are you trying to save here? Yeah, there's 3. Can anybody make a prediction? How could you get it? What's a simple way to finding that? There's 3. How would we know that? What else is there 3 of when you look up there? Yeah, it's the horizontal bar, right? And what does that bar mean again? Divide. That bar means divide. So you're checking that each one of those bars does not divide by 0. This one here that we had last time that was just ridiculous, the reason you've got so many things to check is that's hiding fractions from you. It would look like this in the previous question if we wrote all the fractions down. Okay, so how many division signs are there? 1, 2, 3, 4, 5 that you'd be trying to protect, right? So those are where you'd be looking to make sure you don't divide by 0. That's why that one was so hard, is it was hiding some of them from you. This one hopefully was a little easier because they're not hiding any divisions from you. We're trying to make sure that sine of x does not equal 0. And we already talked about that here. So x can't be a multiple of pi. We're also trying to make sure that cosine of x does not equal 0. And we've already talked about that over here. So x could not be equal to pi over 2 plus pi n. And finally, the last fraction is this big one here, because it's associated with this division sign. And in order to make that equal to 0, I'd have to make sine not equal 0. We've already covered it. We can just chuck that one. We've already dealt with it. So in this instance, those are my 2 restrictions, pi and pi over 2. Okay. We're going to be dealing with sine and cosine for the most part. These are the places you're going to be putting your restrictions on. Multiples of pi, pi over 2 plus other multiples of pi. Okay? Okay, so these ones are a little gentler. I would like you to try them as far as start from the beginning, simplify it, and find the restrictions. Okay, so in this first example, you should have 1 as your simplified version, and cos and sine here both can't equal 0. Sine is on the bottom of 2 fractions, so sine can't be 0. And cosine, if cosine were 0, this whole fraction would be 0. So then I would divide by 0 on the middle bar. Okay. So I kind of prepared you at the beginning to say this is really weird when we first start doing this, but as we go on, you're going to find that you'll like it more because you'll see the answers here. This one, how would you set this up? Like, if you don't know where to start, what's the starting point? Sines and cosines, yeah. Back to basics. Before we simplify this, we're going to cut everything into sines and cosines. So I'm going to rewrite this as 1 over the cosine of x. Maybe I'll just put a little divider there. Divided by sine x over cos x. And this also helps me see where all the problems could be in my with my divisions. There's 3 fractions here, 3 divides that I'm going to have to worry about for looking on restrictions. Now, I'm going to, of course, change this. This time, instead of doing the flip and multiply, I'm going to show you again the way that I had talked about earlier, which is I'm going to look at this denominator, and I'm going to look at this denominator, and look at that. They're the same. If I just were to multiply by cosine over cosine, then that means it's going to be gone from here and there as well. So what I'd be left with is just 1 over the sine of x, and we know that is cosecant x. That would be our simplest form here. Okay? I'm not saying you have to do it my way, but if you actually try to see what I'm doing and you practice that one a few times, when we get the messier fractions this still works. We can knock them out real fast. In simple ones like this, it's probably about the same amount of work to flip and multiply. Here, again, my problems are going to happen when cosine equals 0, and for this entire fraction, when sine equals 0. So I'll have the same set of restrictions as before. Okay, so this time I actually want to show you with the graphing calculator that it's not just hocus pocus. You can actually visualize what's happening here. If I was to try and simplify this one, I'm going to have sine of x times 1 over cosine of x. And that's going to mean I have the tangent of x for my simplified identity. So if I wanted to show you the pictures, here's y equals tangent of x. Okay, which you should be familiar with. Now I'll show you what the graph was that we changed. Sine of x times secant of x. It's the same one. So even though we're doing these changes, now you can see visually that it does actually make sense. They are equivalent. And our restrictions here, that's the only divide that I'm worried about. So if cosine of x can't be equal to 0, what are the restrictions on this? You got a 50-50 shot, really. Anybody feeling lucky? Oops. So cosine is the x-coordinate on the unit circle, so pi over 2, 3 pi over 2. All those vertical spots, that's where it's going to be equal to 0. Okay, so let's start the next one. We'll see if we can get some sense for what are we aiming for when we simplify this. Y equals tangent of x times the cosine of x divided by the sine of x. What do you think? When we're done, what should I see? A straight line? But what's that graph of? Y equals 1. So that gives you some indication now. When you've done simplifying this, you should see y equals 1 as the very last equivalent thing. So again, this is the algebra you're doing. You can see visually with your graphing calculator where you're headed now. Hopefully when we're done this one, we end up with a 1. So give it a try and look for your restrictions. So I ruined the surprise. It simplifies to 1. You're probably so excited to figure this out on your own, right? But when you get there, your restrictions, you have 3 fractions, 3 divide signs that you're looking at. The bottoms of them are, sorry, there's only 2 there. It's cosine and sine. So in this case, it's both the multiples of pi and pi over 2 plus pi n for restrictions. Okay, so at this point, I'm going to hope that when we do cosecant divided by cotangent, that you can do this one. You're starting to get the feel for it. Start by putting it in your graphing calculator. See what you think the answer is going to be, right? Use that graphing calculator. Maybe it'll give you some insight as to where you're headed so that you know if you've simplified it right. Okay, so here's the picture that I ended up with. Does anybody recognize what that graph is? Secant or cosecant? Okay, well, if you're not sure, here's the cosecant graph. Okay, so it wasn't actually cosecant. You can try graphing it against there if you're not sure which one. It's going to be the secant graph. It won't even show up here because it's drawn over top. Okay, so that's what we're aiming for is secant. The algebra might be easier for you to figure that out. So it'll be 1 over sine x divided by cos x over sine x. So now I can see there's 3 fractions, 3 divide signs where I'm looking for my restrictions. Let's go the flipped way then, I guess. 1 over sine x, and I'll multiply it by sine x over cosine of x. And that means I've got 1 over cosine x, which is the secant of x. So that's the algebra. And again, I need to show here that's a problem, and if this whole thing was a 0, that's a problem. So it's not very exciting. It's turning out to be the same for a lot of these cases, but x can't be equal to pi n. It could not also be equal to pi over 2 plus pi n. This here is for, this here is for the sine graph. And this here is for cosine of x, just to remind you where they were from. Okay. So I promise this is the last of our fraction, fun with fractions for today anyways. So see if you can simplify those expressions. And again, it's probably going to be fractions that give you the hard part of doing this. So I'll let you play with them and I'll come around and see how you're doing. So here, if you've forgotten about this way that you can work with fractions, if you're adding the pieces together, as long as you give them the same denominator, you can still go like this and separate that addition. It's a little bit abstract when you look at it with those functions and letters, but it's kind of like if you had 1 plus 3 out of 2. Right? That's 4 halves, which is 2. That's the same thing as 1 half plus 3 halves. It'd still be 2 no matter which way you look at it. So we're doing the same thing, but it's obviously a little more abstract when you don't have the numbers to see. And now I can call this secant of x, and cosine is gone from there, plus the sine of x. So I can't cut this down anymore. That's as simple as it's going to get. And if I look at my fractions here, there's one fraction here I need to worry about, and another fraction here, both of which have cosine on the bottom. Same thing in the original, cosine's the only one in the bottom. So I have to make sure that x cannot equal, what do you think? Where's cosine equals 0? Good, yeah, it's this one, pi over 2 plus pi n. So the same strategy here for simplifying out this fraction. If you want stuff to cancel out, you're going to have to split this one to a couple of pieces. which means that sine is going to be out of that one, and one of the cosines will disappear out of that one. So I'll have cosine of x over the sine of x plus 1 over the cosine of x. And that'll be the same thing as the cotangent plus the secant. So that's as simple as it's going to get. Now I have to take a look at my fraction here. That's my fraction. So there's two possible places. If sine is equal to 0 or cosine is equal to 0, that would be the problem. So x can't be equal to pi n, and as well pi over 2 plus pi n, or your calculator would explode. So we're just going to try calculating some values here. So I'm going to try doing sine of pi over 3 squared plus the cosine of pi over 3 squared. And I get 1. Nice and simple, right? I must have thought long and hard ahead of time to make sure that I got a nice simple answer like that. But let's try it again. Here's another shortcut that's nice to know about in your TI-83. You see where it says entry right there? The mouse is pointing at it right now. It's right above the enter button. But if you want to get the last thing, like sometimes you type it in and you go, oh man, I forgot a bracket, and you have to type the whole thing out again. If you go like this and go second function and ask for that entry, it gives it back to you. So now you can back up and say, oh, this time I'm going to do 2 pi over 3. You like that, huh, Tony? Okay, so 2 pi over 3, and then I'll put the 2 pi in here as well. Oops, that says L. So what was it here? Should be 2 pi. There, okay. I don't know if that saved any time there, but let's try this now at 2 pi over 3. Magic. It also equals to 1. So here's the last identity that we're going to talk about today, which is it's called the Pythagorean identity. And it comes back from the unit circle that we did before. Do you remember how we talked about the unit circle as this? Is that still familiar, or do we need to talk about that? Do we remember this equation is what I want to know. Okay, so this is a circle radius 1. So x squared plus y squared equals 1. That gives the equation of the unit circle. But then the other thing we figured out was down here. We figured out that x was the cosine and y was the sine. So then we can make an identity out of this by combining these two ideas. So instead of x squared plus y squared, I'm going to replace it to be cosine theta plus sine theta squared equals 1. So the Pythagorean identity is the sine, or well, I've got cos there, so I might as well call it cos. It's the cosine squared of theta plus the sine squared of theta, and I just ran out of space, equals 1. Now the reciprocal identities, I know you probably know those already, like you've remembered them. But they are on the formula sheet, so is this on the formula sheet, okay? But we're going to go a step further with it. Sine squared plus cos squared equals 1. Watch what happens if we do a little, I guess, witchcraft, as Tony would call it. I'm going to divide everybody by cosine. So now that I've divided everybody by cosine, I'm going to simplify this expression. So this is going to be sine squared theta over cos squared theta plus 1 equals 1 over cosine squared theta. Can we do it another step? How could I go one more simplification? What could I do here? Yeah, that's tangent squared theta. Tangent squared theta plus 1. And what's 1 over cos squared theta? Yeah. So there's another identity which is true for all values of theta. Tangent of squared theta plus 1 equals secant squared of theta. Okay, and we can do the same thing over here. Sine squared theta. This time I'm going to divide everybody by sine. Okay, see what you come up with if you divide everybody by sine. Okay, so we can call this 1 plus cosines. I'm pushing too hard on the tablet this morning. And it'll give us the last of the identities that we're going to work with today. And the good news again is that this is provided to you. You won't have to memorize those identities, but these are the 3 Pythagorean identities here. So we can use these now to is that better? Okay. We can use these now to prove some new things about these identities here. Like, for example, all of this is apparently equal to the secant squared of theta. How do you think we could prove that? Well, now instead of just simplifying the expression, we can start replacing things. Same way you did like with reciprocals, but now you're going to replace Pythagorean identities where you see them. So when I look at this, and I've had a little more practice, so I see it probably quicker than you do, I can see that there, that's one of the Pythagorean identities, right? So cos squared plus sine squared, what do I replace it with? 1. So this is 1 plus tangent squared theta. And what do you recognize this one now? Yeah, this one here is the secant squared of theta. Okay. Now here's the thing about when you do a proof. You can't move things across the equal sign. You have to pretend that there's a bar here. We're going to practice proofs lots, but I'll just set it up for you now. The reason you can't move across the equal sign, you haven't proven them equal yet. If you don't know that they're equal, you can't move them across. So you have to stay on one side or the other. That's why all my work is on the left side. I could do a little bit on the left, a little bit on the right, but I can never move people across, right? Not until I've already proven it's equal. So see what you can do. Can you figure out a way without moving things across the equal sign? Can you step through and show me that 1 minus cos squared tangent squared x equals cos squared? So your first thing, if you don't know what to do, is to remove those tangents, secants, all that stuff, and try and write them as sines and cosines. So if you can't find an identity, that means you need to start making replacements, get back to basics. So this time that means those cosines will be gone, and I'll end up with 1 minus sine squared x. And I think I'm stuck now. Does anybody see, how am I going to make 1 minus sine squared equal cos squared? Yeah, it's just the one that we've already worked on here. Sine squared theta plus cos squared theta. Because I have proven, like this is a proof that you know is true, that they are in fact equal, you're allowed to move things across that equal sign. So you can call this cosine squared theta is 1 minus sine squared of theta by moving this to the other side. Okay, so last one. See if you can prove those two things are equivalent. Now, you don't always have to go on one side. For some reason, it's kind of like once you get good at this, you want to be able, it's like a challenge to yourself and only yourself that you want to be able to do it all on one side. There's nothing wrong with switching sides now and saying, well, I'm stuck, I don't know what to do. You can move to the other side and go, well, this would be negative cosine x over sine of x times cosine of x. And then this would be negative cosine squared of x over sine of x. They're still not equal. Oops, sorry. I don't know why I keep forgetting to do that. Thank you. They're still not equal, but what I have is I'm actually getting closer to the answer. So what I would hope that as you practice these, you're going to notice that looks an awful lot like this up here that we've already worked on. The difference, however, is that if I put a negative in front, right, if I multiply everybody here by -1, and I multiply this side also by -1, then I'm going to have negative cos squared theta. That'll be -1 and positive sign, so it'll be sine squared theta -1. Right? Or you could have started the equation by moving 1 to this side and cosine to that side. So you will end up with an identity that says those things are actually equal, that this is the negative cosine squared of x over the sine of x. So I know that I haven't actually made either side equal to the original part of the problem, but all that matters is when you're done, the left-hand side and the right-hand side are the same. Because if I wanted to know how do I get from here back to the original, well, now I start marching this way back up to the original, right? So when we do proofs, you don't have to always be on the one side.